Hello everyone. Can one of you please confirm? Just hold on 1 minute, please. Can one of you please confirm if I am audible?
Yes, sir, you are audible, sir.
Okay. Next time. Thank you.
Sir, we have one request, sir, that because of the March, we were not able to see the assignment. Can you extend by Friday the submission of assignment?
Sir, similar request is there from my side also, sir.
Okay. So I extended till Sunday night, but you want me to extend it a little bit more?
Yeah,
Yes,
to
sir.
that coming Friday, sir.
Sorry.
Coming Friday, sir. Friday.
Okay.
So you're asking assignment or homework, sir?
You're asking what?
That homework that we have given, sir.
The theory homework.
The theory homework. Yes, sir.
Theory
Yes,
homework.
sir.
Yeah. Okay. Fine, sir. Then today is
Saturday. So next Friday, sir. Next Friday. By next Friday.
Okay. So next Friday morning. Okay, I'll extend it, sir. I'll extend it next Friday, sir. Okay.
Yes.
Thanks, sir.
Okay, thank you, sir.
But I'll give the next assignment also.
Huh.
Today, tomorrow, I'll give the next assignment also. Just so that people can start working on it.
Okay.
Okay, but there's some overlap, but that's okay, I guess so. Okay.
Thank you, sir. Thank you.
Okay. That's one thing I wanted to ask you, and so I'm hoping that people are also doing the MATLAB assignment. MATLAB assignment has some more time, but please take your time and do that. It's important that we do the MATLAB thing also. Okay. Good. Today what we will do is we'll continue with the branch. Okay. So today I will not be teaching too much about the spec. We'll look at the design of the branch. I mean, branch is a little bit more complicated thing. We have to understand a few ideas and a few concepts. So let's just focus on that particular part. Maybe a shorter class today because of that. And then we'll go to the spec, because until we understand that, the spec does not make any sense. Okay. So just let's recall. Yeah, let's just recall what patch is. So patch is the first step in which the UV is going to tell the base station that, hey, I am here. And using this step is where the base station should understand that the UV exists. Secondly, the base station should be able to perform timing advance and report that to the user. Okay, so these are all the 3 or 4 steps that have to happen. Okay. So today, what we'll look at is, we'll not look at where you put patch and how many patch sequences and how many other things. Those things we'll not look at. So today we'll mainly look at, if suppose I ask you this problem and how do you design this kind of a thing, okay, from a scratch. Suppose I say that I'll give you all the flexibility. How do you design this patch? Okay, we have to let's figure out how we will do it, and then come up with and then try to correlate that with what is there in the spec. Okay, that's what we'll do. Okay. So before we do that, I have to tell you about the sequence called Z-of-shoe sequences. Okay, it's a very important sequences. These have been there from the time of even 3G. Also, Z-of-shoe sequences have been used. 4G, 5G, everywhere the Z-of-shoe sequences are used. Actually, they're beautiful sequences. So essentially, it's a sequence of complex numbers. So this is a Z-of-shoe sequence. Okay, it's a sequence of complex number. This I goes from 0 to, essentially it's an L array. The length is L. Okay. It's a sequence. If you look at the sequence, the absolute value of the sequence is always 1. Okay, the absolute value of the sequence is always 1. What you can see now, because it's a complex, it's e power minus j. If you take the absolute value, it will become 1. Okay, so it's a constant modulus. The constant modulus signal. Okay, why is this important? Constant modulus signal. Why is it important? Because you want to keep the PAPR low, the peak to average power low. These constant modulus signals have a lower PAPR, and when you transmit this over the air, you can increase your average transmit power. Okay, that's why constant modulus sequences are important. Okay, but that's not the only property of this. The more important properties of this is, let me just share you my screen so that I can talk better. Okay, so I'm just going to rewrite this a little bit. Okay, instead of I will go to put. So X of M is called the ZC sequence, Z of C sequence. Okay. So one of the properties of the Z of C sequence is this obvious, and this property is obvious. You take the modulus square, this is equal to 1. Okay, because it's just it's cos theta plus j sine, some cos of something plus j sine of something. So if you take
What is u over here, sir?
Huh?
Ju, e to the power minus ju. What is u over here?
I'll tell you what that u is. Okay, I'll tell you what that u is. Okay, but I'm just giving you the higher level properties. So this is the xm square is equal to 1. So essentially it's a constant modulus signal. This mod the signal or sequence. I'm just reusing it. Okay. The second thing is, so u. What is u called as? 1 minute, I'll tell you the name of the u. Okay, there is no name for it. Okay. So every u, each u corresponds to a different sequence. Okay. So you can pick out u. Each u will correspond to a different sequence. The only thing is u should be relatively prime with L. Okay. So for example, if L is equal to 10, a relatively prime number with 10 would be 3. Okay. So they should not have any common factors. Okay. That's what it is. Okay. This is u should be relatively prime. So on the other hand, if L is itself a prime number, so for example, if L is a prime number, for example, L is equal to 23, I'm just giving an example, then u can be any value. You can take all the value from 1 to 22. Okay. For each of these u, you can define a new sequence. Okay. Agree? Did you understand this?
So but u should also be prime. You can be prime and composite also.
You can be prime or composite. It should be relatively prime with L. It need not be a prime number. Even L need not be a prime number, but u and L should not have any common factor.
Okay.
It should be relatively prime. Okay. The second thing is each value of u corresponds to a base sequence. This is called a base sequence for that u. Okay. So you fix a value of u, you can generate x of m. No? So that is called the base sequence corresponding to that particular u. Is that fine? So what is the most important property? This is called the property 1. I'll put. Okay. This is property 0. Okay. Constant modular signal. Property 1. Okay. Correlation of any cyclic shifted version of the sequence with itself is 0. Okay. So what this means is, you take so suppose you generate the sequence, and you generated the sequence x0, x1, x2 up to, for example, I'm just giving an example, x5 for certain u. Okay. Now you cyclically shift the sequence. Okay. So you cyclically shift the sequence. For example, you cyclically shifted by 1 on the other side. Okay. So you have x of 5, x of 0. So this is a new sequence. Okay. This is a new sequence, x of 0, x of 1, x of 4. You take the correlation between these two sequences. That means this is sigma x of 0, x conjugate of, so I should not write it like this. So essentially, let me just write it for this. X of 0 into x star of 5 plus x of 1 into x star of 0 plus x of 2 into x star of 1 plus x of 5 into x star of 4. This would be equal to 0. Okay. So the correlation of the cyclic shifted version of the sequence with itself is always 0. Okay. So if you take the autocorrelation of the sequence. So what is autocorrelation? Autocorrelation means you take a sequence, for every cyclic shift you find this value. You do this. You do the correlation. Okay. And then you get an autocorrelation. So this autocorrelation is a delta. Okay. Only when the sequences are completely aligned, you get something. Everywhere else it's 0. Okay. Just let me show you actual this thing data. Okay. So this is how it looks. So here there are some other artifacts. I won't tell you those things, but it's actually 0. Okay, so you can think of this down thing as 0, almost 0. Okay, so only when the sequence aligns with itself, you get a peak. Every time else, it's 0. Agree? Did you understand this property? Okay.
Yes, sir.
So by the way, these are also called as Kazakh sequences, constant amplitude zero autocorrelation sequence, Kazakh. Okay, so by the way, this paper is a very small and cute paper. This and the next paper. I mean, actually look at this paper. It's just a couple of pages. I'll try to post this on the our classroom. See if you can read it. Okay, it's a nice paper. It's a couple of papers, a couple of pages. Okay, so here. This is okay. So another, I have to tell you one thing is only cyclic shifts of a given base sequence are uncorrelated. Okay, cyclic shifts of different base sequence need not be orthogonal. Okay, of a given base sequence, so you fix the U and you do a cyclic shift. Then those sequences are orthogonal. Okay, but on the other hand, if you take two different base sequences and you generate shifts with it, they need not be orthogonal. That's what I was also showing in this thing, in the second picture, where this is autocorrelation between two different base sequences, cyclically shifted. They are not orthogonal. Okay, fine. Are these properties very clear? Okay. So the next important property, which we will not use too much, but it's good to know this because this is how they implement this.
So if I miss something, or can you explain what is base sequence?
Okay, base sequence, fine. Okay. So this is the sequence. The sequence is defined in terms of M. So you take the value of M 0, 1, 2, 3 up to L minus 1, you get a sequence. Yes. U is a parameter, na? And I told you you have to choose U as relatively prime to L.
Yes.
You should not divide L. I mean, there should not be common factors. Yeah. Okay. So now for each U, whatever sequence you get is called the base sequence.
Okay.
Okay. For example, you take U is equal to, I mean, suppose L is a prime number. Suppose you take U is equal to 2. Okay. So suppose you take U is equal to 2, you get one base sequence. U equal to 3, you get a different base sequence. Okay. So you can get so many base sequences, as many as relatively prime to L.
Got it.
Okay. So there's another property too. If X of M is a ZC sequence, is a Z of U sequence, then DFT of X of M is also a Z of U sequence. Okay, with, I don't remember the base number. Okay, I mean, I will stop at that point. Okay, I mean, we just don't. I mean, we can even compute. The paper also tells you how to compute the base number of that sequence, the U value of that sequence, and other things. Okay, so this is a very important property in terms of implementation. What this says is, you take the FFT or DFT of a Z of U sequence. Okay, the output is still a Z of U sequence, different Z of U sequence, but of course. Okay, so still the constant modulus thing will be there. So you take a Z of U sequence and you do an FFT. The output is still a Z of U sequence. That means it's a constant modulus sequence. That means the PAPR of the FFT is also low. PAPR of the DFT of the ZC sequence is also very low. Okay, By the way, just to clarify, DFT is the discrete Fourier transform. FFT is an implementation of DFT, a very fast implementation of DFT. So DFT and FFT are the same. So I sometimes, I generally interchange and use them. Okay? So DFT is a more signal processing concept, whereas FFT is an implementation algorithm for the DFT. Okay, I'm just clarifying that if there's any confusion. Okay. Okay. So any questions on these properties? Then we'll start getting into Prach now. Okay. So you understood property 0, property 1, and property 2. There are 3 properties. Okay. So now let us understand Prach. Let's ask this question. Okay. So what should be the properties of Prach? 1. What should the base station do? Base station should identify the user in some way. 2. Base station should find timing advance. Okay, timing advance means the delay between the base station and the UE. Okay, that you should be able to find. There are some other properties which are not so important. Resilience to multipath. Okay, this is another property that's important, that whatever we do, we should be resilient to multipath. Okay. So the question is, how do we design? So now that I told you about the Zeroff sequence, I gave a lot of hint. So how do we design a Prach channel so that all these 3 properties will be satisfied?
The resilience to multipath power control will come, sir, under this.
There's no power control at this point, so it should be. Okay. Another property that I'm going to tell you is just related to what Vijay was saying is, okay, should operate even at very low signal to noise ratio. There will be no power control at this point. Okay. Okay. So the basic idea is, suppose let's say that there are 3. Let's say that there are for simplicity. Let's start with the one user system first. Okay. One user. Okay. So one user is trying to do this. No, let's do with 2 users. It's easy. 2 users. Okay. 2 users. User A and user B. Okay. So user A and user B both are at the same time want to tell the base station that, hey, I am here. The base station should find the timing advance on this. Okay. So what's going to happen? So the base station in this MIB or whatever SIB messages will tell the users that, okay, so will tell the users the length of the sequence, length of Zeroff sequence. Okay. And it will also tell the base sequence. Okay. It will tell some base sequence number, one base sequence number like this. Okay, this comes from SIB message, SIB1 message. Okay, we'll understand this carefully later. Okay, with spec we'll understand. So now both the users, once they decode the SIB message, they will know that the length of the Z sequence is length of the Zeroff sequence they have to use is known, and the base sequence also is known. Okay. So what the users will do is, users will use a random shift. Okay, so user A will use a random shift, maybe K1. User B will use a random shift K2. Okay. Let us for simplicity assume that the K1 and K2 are not equal at this moment. Okay, let's see later what happens when K1 and K2 equal.
Yeah? So here, first time you are introducing this ZC sequence now. So why it will be in the SIB1, sir? SIB1 you have given different sequences.
No. Wait. See, so first what will the user do? The user will decode the SS block. He'll get the MIB message, MIB are messages. Okay, and then they'll decode the SIB1 message. Yes. Once they decode the SIB1 message, in the SIB1 message there will be one integer which tells you what is the length of the ZC sequence they should use in Prach.
Okay.
Okay, and similarly there will be one message which tells you what is the base sequence number that they should use.
Okay.
Okay, it's not the sequence, but is the sequence number and the length that they should use. Okay. So is this clear, everyone?
Yes.
So then the users, what they will do is, once they know the ZC sequence and once they know the base sequence, each of them will be able to compute X of M. Both of them will be able to compute X of M for M is equal to, so let's say the sequence length L equals 0 to L minus 1 and the base sequence number is U. Okay, with that you will be able to compute this sequence. Okay, so then what will user A do is, user A will transmit, I am just being vague here for the transmission, how it will put in the FFT grid and transmit, I'll tell you later. But okay, let's not worry about that. Okay, user A will transmit a shifted version, a cyclically shifted version of the sequence K1 with K1. Okay, K1 shift. Okay, so for example, if the user one chooses K1 is equal to, example, K1 is equal to 3. Okay, and then what will happen? It will start as X of L minus 3, X of L minus 2, X of L minus 1, X of 0, X of 1, so on. Okay. User B does a K2 shift. Example, what do you say? K2 is equal to 1. Okay, so he randomly chooses this. Both of them randomly choose. Then this user B will transmit this. Okay, this sequence. Is this fine? Okay, so both of them are transmitting the sequence at the same time. So what will the receiver get? The base station will get some of the sequences, some of the cyclically shifted sequence. It will get sequence 1 plus sequence 2. Okay, so this is sequence 1. This is get sequence 2. Agreed? Any question till here? Okay. So now what will the base station do? Okay, so now what will the base station do? Let's understand this. Okay, so for now let's assume there's no timing advance. I mean, both of them are very close to the base station. Let's assume that. Okay, let's make a simplifying assumption for that. Okay, so first of all, now how will the base station identify what is the shift that the user 1 used and what is the shift that the user 2 used? Can anyone tell me?
So they will, at the base station, it will be convoluted with that sequence itself.
Yes.
And with that shift, where with itself, it will have a delta function. Rest it will be 0, sir. Then
Yes.
it will know that
exactly. That's absolutely right, sir. So what will it do is, base station knows the base sequence because it only sends the message, base sequence it knows. Base sequence X of M. Okay, what will it do is, it will first correlate Y, the received sequence, with X of M. Okay, it will see if it gets a peak. Okay, it will not get a peak in this particular case because both of them are cyclically shifted. Then it will do correlation of Y with X of M shifted with 1. Okay, it will shifted with 1, cyclically shifted with 1. It will get 1 peak. Okay, so it will get 1 peak. Then it will do correlation with X of M shifted with cyclic shift 2. It will not get any peak. It will do X of M shifted correlated with X of M shifted with 3. You will get 1 peak. So on and so forth it will do. It can do this in a very, very intelligent manner. You don't have to do it this way. You can do it using it FFTs. So essentially what it will do is, okay, so what will happen now, if you find this correlation with different shifts, okay, so as a function of shift, if I put as a function of shift, you will see a peak in 1 and you will see a peak in 3. Agree? Okay, so after correlation. mean, there's a lot of lag today. I don't know for okay. So once it does this, then immediately it knows that it will see the count the number of peaks. If there are multiple more users, they will find so many peaks. Okay, it will immediately find that there were 2 users, one with shift 1 and one more with shift 3. Okay. Suppose up to this point it's able to do this. Then what will the base station do? The base station will tell, now it will send a message, it will broadcast one more message. There is after SIB also there is something that happens, we'll discuss this in Praj. What it will do, it will broadcast a message to all the users saying that, hey, I found 2 users. One of the users used shift 1 and another user used shift 3. Okay. So it will say the user who used shift 1, please transmit in the uplink in this resources. The one who used shift 3, please transmit in the uplink in these resources, in the different set of resources. Okay. That way it will be able to identify the users. I will also tell the user, it will also give a user number to each of them at that point. Okay. You understood? So essentially the users are identified by the shifts that they have used in the Xerox sequences. Is this clear? I will make this more formal when we do the Prac properly. Okay. Is this clear?
Sir, when both are having same shift, then what will
I will come to that point. We'll come to that point, Chitranjan. Yeah. Okay.
So sir, and here we are assuming both are having the same K. Both are same K.
Same U.
Yes, U.
Yeah, same U. Yeah. For now, I'm just making some simplifying assumptions so it's easy to understand. I will tell you what happens. I mean, actually, the same U will not be used. I'll explain. Okay. So at this point, one thing is simple. If both of them chooses different cyclic shifts at the base station, I'm able to identify this thing. Okay, I'm able to identify the users. Okay, I'm able to identify the users. So now let us understand how timing advance will be calculated. Okay. We can, to do this, we can just focus on one user. Okay, one user, and the same thing holds for other users. Okay. Okay. So what will the base station do is, the base station in its SIB message tells the UE. So at that point, before the patch is transmitted, the UE knows exactly the time resource grid. Yes, it knows the time resource grid. So now what will the base station tell the UE? The base station tells the UE, please transmit in this OFDM symbol number. It will tell patch. Okay. So suppose the OFDM symbol starts here. Okay. Let us assume, I mean, let's do one way delay for starting. So then the UE will transmit the patch here. UE will transmit the patch here. Okay. So by the time the patch reaches the base station, what will happen? There will be some delay. This is where the patch is received by the base station. Agree? I mean, I'm showing so much delay, but it won't be so much delay. This delay, of course, depends on the cell size. Okay. So now, how does the base station find out this delay? See, again, it uses the correlation properties. How will it do? It correlates. It correlates starting from here. Okay, nothing will come. Nothing will come at some point. So this is, it knows that this is the time t equal to 0. It correlates at this point. Nothing comes. Then it goes here and correlates. Okay. Then it goes slowly moves, and at this point, what will happen? You get a peak. Okay. So using this delay, it will be able to find the timing advance. Okay, so it knows. I mean, I shouldn't say this as timing advance. This will be actually twice the timing twice the delay. Okay. Twice the delay. Sorry, today the network seems to be very bad. Okay, why twice the delay? Because in the downlink there was also a delay, and the uplink also there's a delay. So essentially, the downlink itself, what will happen is the UV's frame is delayed by this delay already. Okay, and from that point, reference point, it's transmitting uplink, so there will be one more delay that's added. So the twice the delay will be added in the timing. In this will be corresponding to 2x the delay. Okay, is this fine? Okay, so from the starting point where it finds a peak, it will be able to find the timing advance and the sequence which and the cyclic shifted version of this, which gives you the what do you say, the what do you say, the cyclically shifted the cyclically shifted property tells you which sequence works. Which cyclic shift was done by the user is known. Okay, any question?
Sir, here it should be one delay. While doing the timing advance, it should be the 2 delay, because we are doing at the base station. It is coming from the UV. It should be 1 delay.
No, it should be 2 delays, sir. Why means? Let's think about this. I mean, this will be 2 delay. The reason is the base station's time is absolute. Okay, the base station has a notion of time t is equal to 0. Okay.
Base station timing, if you take reference time, then it is 2 delay. Okay.
Yeah, that's the thing. That's the point. Okay, because the UV is already by the time UV records its MIB or it blocks on the SSB, already there's 1 delay, and from that reference point, it's doing 1 more delay. So there is twice the delay. From the UV perspective, is 1 delay. You're absolutely right. Okay. Any questions before we proceed? Okay, so there was one question. So what happens when both of the users they're randomly picking some number? They're randomly picking the shift, the cyclic shift. What happens if they pick the same shift? Okay, so when they pick the same shift, the base station will be able to identify only one shift. It will tell I found one user with one shift. Okay, and both the users will feel that they have found the shift. Okay, and then both of them transmit at the, so there are 2 ways of resolving them. And then next time what happens, both the users will both the users will transmit at the same time on the uplink. Yes, and they'll collide and both of them will not get anything. They'll do sometimes one way what will happen is after some time they will time out, and then they do the patch again. That's one way. There's another intelligent way of doing this. I will tell you that is called something. The 4th step of patch process is called contention resolution. Okay, when you have 2 users who chose the same Xerox sequence, same cyclic shift, there's a specific way of resolving that. Okay, that time we will do it exactly when we do the 4th step of the patch. There's a way of resolving that contention. Only one of the users will be selected. Okay.
Sir, if the shift remains same for 2 users, but the timing advance is different, then the collision may not happen.
Yeah, collision might not happen, but you should understand the timing advance is generally smaller than the shifts, much smaller than the shifts. That's what happens. So before, I mean, this will become clear. First, let's just once talk about multipath. This will also clear your idea of that. Okay. So, okay. So until now, what did we assume till now? We assumed that you transmitted this. This is the sequence that you transmitted, and the base station guy nicely got this. Yes, but that's not what happens in reality, now. What happens because of this multipath? Okay, because of multipath, what does the base station get? The base station will get a combination of this plus this. Some cyclically, some shifted versions of that. Yes. Okay. So when the base station correlates, how does it look? Of course, all of them will have different powers. Okay? This will have power P1, P, because the multipath, all the taps will not be of the same power. They will have some decaying power. Okay, decaying power, which we don't know where the peak occurs. Okay. So when this happens, if you now do the correlation, what will happen? You'll find a peak, and then a smaller peak, and then a smaller peak. Agree? Depending upon how much is this multipath. Is this clear?
Yes, sir.
Okay. What happens because of this? So so this imposes a very difficult constraint for us. Okay. So the number of taps you can get, the number of taps or time dispersion is proportional to the cell size. Okay, if you have a larger cell size, most probably you'll get a lot more, a little bit more taps compared to a smaller cell size. Okay? The number of reflections will be larger. Okay, you'll transmit from a far off distance. Okay, so what should you do? So suppose the second user chooses a very close by cyclic shift. Okay, the first user is this. Okay, the second user chooses a cyclic shift which is very close by. Then the second user will come here. The second user will have a correlation here. Then the UV base station will not know if that's a user or a multipath. Okay. So base station has to distinguish between user and multipath. Just hold on 1 minute, please. I ask them to switch off for something. Just give me 1 minute. Sorry. Okay. So base station will have to distinguish between the user and the multipath, which is not possible. Okay. So what should happen? What should be the smart way of doing this? So if the UV1 chooses a particular random number, a particular cyclic shift. So suppose he chooses the cyclic shift 1, and you know the multipath dispersion is approximately 1 or 2 cyclic shifts, corresponds to 1 or 2 cyclic shifts. Okay, maybe let's just for example say 3 cyclic shifts. 3 shifts, it's as wide as 3 shifts, the multipath. Okay, then the second user should not take anything within the 3 cyclic shifts. Okay, it should only choose, so essentially 1 it chooses, then it can choose only 4. Then only the second user will be resolved. On the other hand, if the second user chooses 2, 3, then it will become part of the multipath of the first user, and there'll be conflict. The base station will not know what to do. Okay, so what they do is, so what does the base station do is, while in the SIP message, it will also tell you, this is part of the design, the cell design. Okay, you should understand how much will your multipath be, and there's something called as restricted sets. Okay, so what it says is, so instead of allowing all the users to randomly choose between 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, what it will do is, it will allow users to choose 1, 5, 10, 15, 20, 25, so on. So the users can choose any random thing between in this set. Okay, so the gap here is 4. Why is this gap put? This gap is put mainly so that multi-path and the multi-users are not conflicted with each other. Okay, so how much is this gap depends on the delay spread. Okay, so this is something that the base station also informs in the SIB1 message. There's a very specific manner in which it informs. Is this fine?
Sir, how then it distinguishes between its own multipaths?
That's a very good question. Okay, so now suppose once you finish this, once you do this, at least now the users are separate. Now how will the correlation look? It will look like this. Okay, there's one cluster here, and then the second user will have a cluster here. Okay. So now the question is, which of this will they? So this is the delay profile. Okay. So the question is, of course, it will know. I mean, these peaks will only come for that particular, what do you say, cyclic shifts. Okay. So it will be able to find the cyclic shift, but it can choose any one of these things for its delay, for its timing advance. It doesn't matter. Okay. Generally, what it chooses is, it chooses the one with the highest peak, because that corresponds to the highest energy. Fine. Does it make sense?
Yes.
Okay. So now let's get back to sequences. Okay. It's e power minus j mu m plus 1 into m by L. Okay. So what did I earlier tell? So for a given base sequence, technically, so if the base sequence is fixed, so how many cyclic shifts can you have? How many cyclic shifts you can have? You can have L cyclic shifts. L cyclic shifts are possible. Sorry, L cyclic shifts are possible for a given U. Okay. So, but what we now learned is that all L cyclic shifts cannot be used because of multipath or because of the delay spread. Okay. So, how many cyclic shifts can you use? Approximately, you will be able to use L by the delay spread. Okay, whatever the delay spread converted into integer. Okay, properly with the proper sampling factors and other things. Okay. So only those many sequences are there. Okay. One thing you observe is, as the number of sequences decrease, there's a higher chance of collision. Yes, now if there are only 2 sequences and there are 2 users, there's a very higher probability of both of them choosing the same sequence than compared to there are 20 sequences and there are 2 users. That is very obvious. Is that correct? So if you want to reduce the collision probability, you have to increase the number of sequences. Okay, but the number of sequences you get for one base sequence depends not only on depends on the cell size. If the cell is larger, then the number of sequences will be lower. On the other hand, when the cell is smaller, the number of sequences will be larger. Okay, so how do you get more more number of sequences so that you can prevent collision? So what they do was, not only they use one base sequence, they use multiple base sequences. So they get a few cyclic shifts from here. They get a few cyclic shifts from the other base sequences. Okay. But one thing we learned is that the base sequences, I mean, the different base sequences are not orthogonal. So therefore, the cyclic shifts of the base sequences are also not orthogonal. So what they bank upon is the fact that these multiple base sequences are used by users who are in different locations, so that the timing advance is separate, and they get separated out in the multipath profile because of the delays, so that they don't collide. If they collide, then there's nothing you can do about it. You understood this? Okay, so I mean, when you transmit the same base sequence with different cyclic shifts, you can separate down using correlation. But now you have multiple base sequences. So if two users transmit different base sequences on the same time, the same timing advance, okay, then there's no way you can recover both of them. Maybe you can recover one, but not both. Okay, but what is the probability that happens? The probability that happens will be very, very low. Okay, there's a particular way in which they choose the sequences also. Okay, so that is how they use multiple base sequences so that they don't collide. Okay, is this clear? Okay. Okay, so essentially Zerovsky sequences and their properties form the basis of Pratch selection. Okay, just go to the slides once. My computer also became slow.
LTE also same way happens, sir.
LTE. So Pratch, what our Pratch I'm teaching is very, very similar in LTE also. There's almost no difference. I'll tell you a few differences are there, but not too much. Okay. So this is what we were discussing. Okay. So this is another thing that we should design. So there's something called Pratt slot duration. Essentially, this is a slot in which nothing else is transmitted. This is called the Pratt slot duration. So we'll look at this tomorrow. I'll tell you how this Pratt slot duration and other things, this guard periods and other things are designed. So, but I hope you understood the basic idea of this thing. The whole basic idea of the thing is that they use the correlation properties and the cyclic shifts are orthogonal. Okay. So they use both these properties to design the Pratt. Okay. So in the next class, what we'll look at is we'll look at how the different base sequences are used. We'll go into the spec part of things. Okay, what are the different Pratch formats? What is used for LTE? What is used for 5GNR? Why is this particular choice made? I mean, how is this related to the cell sizes and other things? Okay, so this is kind of important. And how does this work in low SNR? Okay, these are the things that we're going to look at in the next class. Okay, so what I'm going to do is I'm going to post one LTE. So there's one beautiful book on LTE, which has a very good description of Pratch. Okay, that it actually explains the theoretical underpinnings of Pratch. I'm going to post the chapters in the classroom, that particular chapter. Please have a look at it. Okay, that will also give you a better idea of why these particular things are used. Okay, while it is for LTE, the same philosophy is still the same, so it should not be it should not be an issue. Is that fine?
Yes, sir. Yes, sir.
I'll do that today.
Sir,
Vijay, tell me please.
So can we like create the artificial environment of multipath channels and all? Can we do that one, sir?
In MATLAB, yes. In this assignment, sorry. In this assignment, what do you say? One of the things is you are using a multipath channel, no?
Yes, sir.